All right, so let's use everything we've learned so far and apply the glue constraint to this little scene here. And what we have here is a statue and, a pretty scary ball that runs into this statue and destroys it. So this is the goal that we had in mind here. And look at the behavior specifically. The lower part is still staying intact when the sphere hits, and only the upper pieces are actually breaking off. So this is something you should be able to do at this point. It's not, just 2 or 3 nodes. It's quite a lot of nodes we need for this. So it's a bigger one, but this is a good homework for you to test what you know so far. So as usual, the idea with the homeworks is you try to do this yourself first, a bit of a practice to figure out how much you already understand and how much you don't. So try it out yourself first and then look at the solution. So what I have to start is really just this geometry here that comes in as an alembic. It's a low poly geometry simply to, keep the simulation fast. And the only thing that I added on top is a little bit of lighting. So I have an environment light, the built-in Lenong HDR for the filler, and the main light is a grid that, flies up here. Nothing fancy, just something to make it look more interesting than this boring thing. A little bit of light goes a long way. All right, so let's start. Since the geometry comes in from outside, the first thing we always do is check the size. So let's bring in a Tommy as usual and see how big our sculpture actually is. So let's move him to the side. You can see that's a pretty big sculpture. Now maybe that's what you want, but that's not what I want. So either way, it's good to always be sure that you are aware of your scale. So let's scale this down a little bit, maybe to something like this, and then we're good. Thanks, Tommy. The next thing is we of course have to convert it because this is an alembic and we can see this comes out as a single point. So let's convert it with a convert node. So let's go from here. This is the preparation. The first thing, of course, we need to do is to break this thing up. The classical approach is to use a Voronoi fracture. And this is perfectly fine. All you have to do is you have to make sure that you have some points. In this case, we want to scatter them inside of the geometry. So maybe we do this with an ISO offset and we increase the resolution and then we just scatter inside and then we have a lot of points. We can try to, turn off relax iterations to give it more variation, but usually that will be not enough. So when we use this technique, and we can show this, for example, by clicking here on the piece visualization, they're pretty even. There are ways, of course, to fix this, but what I will do, because it's much faster and easier in this case, is I will use the RBD material fracture. But of course, if you solve this problem with the classical fracture, that's even better, because then you understand better how it works. I want to look into the RBD material fracture though, because this will do a couple of things for us and we still have to create enough nodes anyway. So let's save a little bit of time. So what we can see here is that it uses an internal way of breaking this thing up. And as you can see, it's very uneven. The reason is that the noise that is used here is not set up in a good way. So maybe what we can do is, first of all, let's scatter more points and we can see we already have 2 different fracture levels. So let's maybe turn the second one off for now. And the first one, you can really just offset the noise if you want, and then you will get a different result. That's perfectly fine. Just play around and find something that works for you. What I want is I want to lower the volume resolution because I noticed that then the feedback is quicker, and I will increase the noise frequency. What can help here to understand this better is turning on the visualization up here with a primary volume, which shows you what kind of noise comes out of it. And this will help you to adjust those things a little bit better. Now, actually, this doesn't look too bad. So let's simply increase the number of scatter points, maybe to 15. And let's look at the result by turning the visualization off. That's not too bad. It's just a bit boring because we probably need more points. So let's create another fracture level. There you go. And this has basically the same problem. So now what we can do is we use the primary volume again, but this time we look at the second volume that is used, or the second noise inside. And again, we can just move it up, or we can change the resolution. What helps is lowering the volume resolution, or increase the frequency. What can help is to lower the volume resolution to make this quicker. and maybe I want a bit more variation, so I increase the frequency again, maybe something like 10, 10, 10, doesn't really matter. So let's see what came out of this. Let's turn off the visualization again, and yeah, that doesn't look too bad. We could turn on chipping, but usually I'm a bit careful with this one. I would rather maybe add an additional level if I wanted, but I think I leave it at that. Let's not spend too much time on this. Of course, this is something where you can put much more love into. About the detail we'll talk about later. I think I would start with this first to get the other settings done, and I think that's for now everything we need. Now, what's more interesting is what happens next. And we will just create an RBD bullet solver to see what's happening. And this is what I do quite often. If I'm not sure what the best next approach is, just move ahead with what you know and not what you don't know. And then the gap will show itself. I connect the constraints already, and let's see what happens. And what happens is it falls down. And that's because we don't have a ground plane yet. So let's turn this on in the bullet solver. There you go. And now it stays together, which is nice. And that is because, why is it not just falling apart? Because we connected the constraints. And the constraint settings are actually here under constraints, and we can see we have a glue constraint. Before we move on, a quick note, there's something that the RBD material fracture complains about, so let's check this. The input geometry has holes. This may result in bad or missing geometry. Now, this is something not to ignore. In general, this is something you should check for. Even though it doesn't seem with this geometry, this is now actually not watertight, and you can see that at the bottom. The best way to make sure that this works, in my experience, is to use a polyfill and set it to triangle. This almost always works, because even the most weird holes will be able to be closed with triangles. And there you go, this worked for now, and now the error should be gone. And let's quickly test this without the constraints, just for fun, to see if this whole thing falls apart like it should. And I think the distribution of pieces isn't too bad actually for our example here. Let's actually turn off the piece visualization. It's a bit annoying, so this works fine. Okay, so what we wanted is we want to destroy this thing by throwing a ball or whatever against it. So let's create a ball with a sphere. And I usually use a polygon sphere. So triangles are fine. And let's move it somewhere where we like it. Maybe adjust the size a little bit, something like that. Now, usually when you have some kind of projectile, you have two options how to approach this. And both have good reasons to be chosen. One is I would animate this sphere as a static object, meaning I would animate it as a collision object and it will not be influenced by the simulation. The disadvantage of this would be that the sphere itself will not react to the simulation. It will just fly through as if nothing would happen. This is useful for cannonballs and stuff like that. But in this case, I want this sphere to be slowed down by the impact, which means I need to make it an active object. This means it has to be part of my simulation, and I have to merge this together with my other piece that is already active, which is of course the sphere. Now, by the way, let's reconnect the constraints. I almost forgot about that. And when we rewind, and of course, now notice we are on frame 1001 because of course we talked about this because of pre-roll and all that. It's very common to have your scene starting at 1001. We talked about this in length before. So where is my sphere? I'm actually not sure why we don't see it. We should see it. But one of the problems here for sure is that whenever we will do something with this now, I would recommend to pack the geometry first. Now for the sphere, that's easy. We can use a pack, but I will get used to using an assemble and make sure to turn on the create packed primitives. For the sphere, that's perfectly fine. Maybe we change the name to something like ball, and you can see now it shows up, which is great. The same we can do with the RBD material fracture, so our statue, but be careful here. If we do this and we do it the same way, maybe we're clever and recognize that we cannot just copy the assemble with the same prefix, because then all the pieces would be called ball something. So let's call it statue. And if you would try to simulate this now, you will see that everything just falls apart. So the constraints that we had before, and let's quickly turn off the assemble, will not work anymore. So the pieces should stay together because they have a glue constraints in between. But as soon as I use the assemble here, the whole thing doesn't work anymore and it falls apart. Why is that? Well, that has to do with the name attribute. This assemble, as we've seen, overrides the name attribute of each piece, but we shouldn't do that because the name attribute is already set in the RBD material fracture. So let's make sure we actually keep the packed, but we do not want to create a new name attribute. We use the name attribute that already comes from the RBD material fracture. And here we go. Now we're back to the piece, number. So let's test this for now. And at least the statue stays intact and our sphere rolls away. What's the problem with that sphere? Well, it doesn't have any velocity. So that's easy to do. And that's one of the reasons why we should pack this. As soon as we assign any kind of attribute, usually it's a good idea to pack the geometry before that. So in this case, all we want to do is adding a velocity, pretty straightforward. And the direction, even though we can't see it again, is -z. So that means we give it something like -10 maybe in z. And let's see what happens. Yeah, that's not too bad. Maybe a bit too strong. Maybe -5 will do as well. Yeah, okay, maybe -8. Somewhere in the middle. Okay, so seems to work. Two problems. First of all, the whole statue falls over, not what we wanted. And secondly, even if it falls over, we would expect it to break apart and not stay in one piece. Well, let's fix the second one first. And that is simply because by default, the glue settings are a bit too strong. So we find that in the RBD material fracture, 10,000, which is way too high. So let's try 1,000 instead. And also the level multiplier means that for each level where, more pieces are broken up, the smaller pieces will be 5 times stronger in the glue constraint than the one before. I would lower this as well, maybe to 2. Of course, you have to play around in your case with what you want. So let's see what happens if I run this again, this time with a lower glue constraint and a lower multiplier for each level. And it looks like this, much better. At least we have pieces flying apart. It still falls over though, and this is of course because there is nothing that holds it in place. And usually, sure, probably statues are not connected to the ground as far as I know, but in our case it makes sense to do this just like we would do with the wall. So we know how to do this. We need to create a group first for the pieces. First of all, of course, we want to do this either on the primitives or the points. It is the same because we have packed primitives, and as you know, they are primitives and points at the same time. I think I usually use points. Let's call this inactive. And let's choose an area. That's actually not too bad. Maybe a bit lower. There you go. This is the stuff that we want to deactivate. And of course, what we want to do is we use a point wrangle. And let's call this active 0, where we want for all the points that are in the inactive group, we set the attribute, the integer attribute active to 0. Now, some of you might already notice this is actually not, this will not work. Let's see what happens. Let's run this and nothing happens anymore. What did we forget? Well, you probably guessed it. The reason is that as soon as we assign an attribute, even though it's 0, that we never used before, then all the other pieces that are not in the inactive group will also get this attribute with the default number. And guess what? The default number is, it's 0 as well. So what's important in this weird setup is, even though it seems strange, before we do anything, we should activate everything, even though technically it already was activated. And let's make sure that it's really activating everything, not just the inactive group. And then it looks like this. And this is why I did it after the merge, so that the sphere is activated as well by default. Feel free to do it differently, but this is my logic. This is not, of course, the only way of doing it, but I hope you understand the logic behind it. So now let's see what happens. And that looks pretty good. What I would play around now with is actually a better number, because I actually want a bit more destruction. So I might lower my primary strength a bit further. I don't know, 500. This is a point where you simply have to do trial and error. There's no magic to it. There you go. Maybe you like this behavior. Maybe you don't. Play around with the numbers. There's nothing more to it. I think I will try a number that worked for me when I tested it, 700. I have no idea if it will also work in this case. So this is great. This might be exactly what I want, but in my case, maybe I'm not happy with the overall behavior. And what I don't like is that the sphere, yes, it breaks our statue, but it doesn't feel very strong. You know, it instantly stops completely and, you know, falls down in front of the statue. What I want to is to give it a bit more oomph. Of course, what I could do is I could increase the velocity. That's true, because this will result in a different result. Here you can see it rolls a little bit over the statue, but I have other options. I can change the energy distribution between the two objects, and for that, of course, we can use density or mass. As usual, you can use density, and then it will be a calculation of density multiplied with the size of my objects, and then you get a mass internally calculated. And this is something you can, for example, do with an RBD configure, for example, if you don't want to do it by hand. I personally don't like that for many reasons. I prefer to do it manually, and I don't even use density. I use the end result, which is mass. So I don't let the solver calculate the mass, but want to write the mass myself. And for this, first of all, I have to make sure that I use the override attribute, because only then it will allow me to override the mass inside of the simulation. And the reason I like that is that it's, in my experience, easier to control by the numbers, because it does not take the size of the objects into account, and I can more freely directly set the numbers the way I want. So for example, if I set the mass of the sphere to exactly 1 and the mass of the pieces of the statue to, let's say, 0.1, then I don't have to, you know, guess what the distribution will be. It will be exactly 10. Be really careful, by the way, because when I tested this, I made the mistake of mixing up the mass of the two. So the left one is actually the sphere. It has a higher mass, and the right one is the statue with a lower mass, even though in my network they are the opposite side of each other. So be careful that you actually set the right mass. And now the distribution is that the sphere is 10 times stronger, so to say. And when I run this, it looks like this. Okay, it's not stronger than before because that's just how we started. But now we know the distribution is 1 to 10. So I increase the mass of the sphere by 10 and run this again. And you can see now it's 10 times more powerful, which is probably more what I wanted. Okay, maybe it's a bit too strong, so maybe 10 is a bit too high, maybe 5 is fine. And this is what I mean. I have now a lot of control and can really control how it behaves. Now we could stop here. This is perfectly fine, everything we need. Let's add a few small bits and pieces here and there. What I can also do is I can add a little bit more detail on the inside of the pieces. In this case, this can be done directly in the RBD material fracture under detail. And I can activate just the interior detail. And actually, while we're at it, why not add the edge detail as well, which will make it pretty slow, but who cares? And then the detail size, I already know I have to halve to make it look good. But this is something you have to play around with. And here you can see this is how it will look like. For now, I think that's fine. And the simulation shouldn't have drastically changed, because we still simulate, again, not with the geometry that we see here, but with the represented geometry. So this is why an additional detail shouldn't matter, but let's see. And if I run this, actually the behavior has changed, you know. So what we can do now is increase the mass again, maybe by 3 times. Maybe 10 would have been enough, so 2 times. And there we go. I think we can leave it at that. I actually like that. Look at the head. The head breaks off, and then it breaks again once it reaches the ground, which is okay. So one last thing, because I noticed that happened to me in my tests. In this case, you don't see it, but when you look at the constraints here, there are a couple of constraints that were built between the inner pieces and the pieces of the arm. This is something you can also change in the RBD material fracture. The constraints, there is a certain search radius. So if you lower this, then it will not find as many connections, but it also will not find the connections between the arm and the object. In our case here, that didn't matter, but maybe that is something you run into and something worth knowing. So yeah, so if you had something like that, then that's great. As you can see, there's quite a lot to make this work. And this is the thing with RBD. Each step is relatively easy to understand, but you need so many steps for even such a simple simulation, that this is what makes RBDs so tricky. They are pretty complex, and especially for bigger projects, those networks can become really big. So either way, thanks very much and see you later. Cheers.